So let's talk about Tcl Tasks. Tasks are a layer on top of the Tcl Threads package. Each task is a Tcl thread, so there's a one-to-one relationship. Tasks mimic procedures in the sense that they are said to be called and are given input parameters that are in the form of arg lists, just as all procs, methods, and commands do. Tcl threads typically send data between threads in the form of a script. However, Tcl tasks use arg lists. Since Tcl is a dynamic language, one can always send scripts in an arg list, and the task can simply eval them, so we're not losing anything by sending arg lists. But by being arg list centric, we would hope to make tasks easier to use by using the familiar arg list interface that procedures, commands, and so forth use. Since a procedure can be called any number of times with the same or different arg lists, in order to mimic this with a task, we use a job queue. Tasks, being threads run concurrently, have their own program counters, stacks, etc., and instead of pushing an arg list onto a stack, running a procedure, popping the stack, and returning a value, a task waits for an arg list to be entered into its queue, removes the arg list, and produces some result, which it then returns to whichever task or thread had called the task. Like a procedure, it can be called again. And so the task is normally and by default run in a loop, which gets a job, an arg list, returns a value, and then goes back to get another job. This is what makes a task look a lot like a procedure call. There is one difference, however. Tasks are not reentrant, and unlike a procedure, cannot recursively call themselves. Tasks use a set of TSV shared variables to maintain their state and to pass data between callers and the tasks. Tasks can run singly or independent of other tasks, or several can work cooperatively by getting their jobs from a single FIFO queue. So, the task command, actually a proc, but I use the terms interchangeably, is used to create a single task with a queue. The new task can be created with its own queue, or it can share the queue of another already existing task. The tgroup command is used to create a group of related tasks that all share the same queue. And finally, the tproc command is used to convert a proc into a task group. Note that task and tproc both begin with a capital T. All the other task procs use a lowercase t. Anyway, it's now time to look at some code. In our other tasks videos, we concentrated on using the tproc command. Here we will look at using the task command and tgroup in more detail. Returning to our testbed, we have our init code from our other videos where we load our tasks module, open the console, and create a TK button. We also define our timestamp procedure and output the version of Tcl and the pointer size to distinguish 32 and 64-bit Tcl. When we run, we use Tcl kits so we can choose which Tcl version we want to use. Let's fold the init code to concentrate on the example code. Here we have 3 sections of code folded up that will run sequentially using the task command and also using tgroup. We can choose by setting the variable test to one of the 3. We have a 3-way if statement indented to the right so it doesn't obscure the code we want to demonstrate. We will be using the proc sum, which returns the sum of its args, but first uses the xwait busy wait procedure to simulate about 15 seconds of heavy compute so we can monitor what is happening in our system using the Windows Process Explorer program, which looks like this. So first, let's unfold sequential since we set test to sequential, and let's look at this. All this does is calls sum, gets a result, and spits it out. So let's run it. And we're using a 32-bit version right here. And we can see over here that took 12 microseconds. Let's run it a second time, and notice that if I try to move these windows, nothing happens. And it gives us a busy signal, says not responding. And finally, after it finished, then we got our events came through, and we see that those windows moved. Next, we'll switch to this version down below, which uses the task command. Here we create a task called sumTask that has one option to import tasks to our thread without needing to namespace qualify our procs, plus our import list, which will import the proc sum from the main thread into our task. Our task has a script with 3 statements. The first is twait with a single argument, argv, which will be set to the next arg list that arrives in our queue. It then calls sum using the argument expansion operator to compute a result, which it then returns to our caller. The result of the task command was to create a thread using the supplied script, but it also sets the variable sumTask to the thread ID, which we use to call the tasks. Or task singular, I meant to say. That we do here using the tcl command. Notice that we supply the sumTask variable with a $sign in order to use the value, which is the thread ID. In this example, we're going to call sumTask async, and we're going to have a result variable, and here are our arguments. This is a little syntactic sugar that's optional, just to make it a little easier to see what's going on and divide up the result from the input arguments. Because we called it async, we will follow it with a twait on the result variable. So let's run our program. We can see that we got a result of adding up 1 through 5, and it took 12.5 seconds. At this point, we can type in our tdump command, and we can get some information. We see that we have a task, sumTask. We also have a thread, the main thread. So we're running 2 threads. We see our result here. We've called it 1 time so far, and this is the variable that got the result. Let's quit this and run it one more time here. And notice that now we can move these around freely, because our main task, which is in the main thread, is not burdened now with computing that result as it's going on in another task. In fact, if we run it again, while it's running, we have the ability to type in a command. In fact, we can see here that the count is 1 because it increments that as soon as the twait command over here, as soon as he retrieves a value, he increments the count. But you'll notice there's no result yet because it was still computing while we typed in that command. But we had no trouble at all running a command from the console while that thread was crunching along in the background. Okay, for our third try, we're going to use tgroup, so we'll unfold this text here, and we see that we're also going to call this group sumTask. We're going to tell it that we want 4 tasks. Once again, we don't want to have to specify tasks : everywhere. And we're going to import sum, and we're also going to set a global variable tdebug inside the thread itself to -1, so that if we have any debug statements, they won't print out. Our code is the same as we had in the single task version. Following that, we're going to call the threads plural, because this is a group of tasks. There's 4 of them, and they're going to cooperate on working on items that we send into the queue using the tgroup and the for each version, or for each subcommand of the tgroup command. Once again, we can go over to our wiki page under the section tproc, tgroup, and utilities. We can see the documentation for the tgroup command. The first argument in all cases to tgroup is a group name, and the group name will be used to create tasks that have that group name with the number 0, 1, 2, so forth following for however many tasks we create in the using the tasks. When we can use -call, -for each, or -run in order to actually feed tasks into this group of tasks. I should say feed arg lists into this group of tasks, which will each compete to grab an arg list from the queue, and whichever ones get there first will pull an item off of the queue, process it, and return a result back to the caller. The results in this case, however, go into a group name array, or I should say an array that uses the group name, and it has indices rvar, star, where star is going to be going 0 to n-1 for however many arg lists we've worked on. We can also go back and see what the arg lists were, because that's stored in the group name array as well. So looking at our code here, we use the tasks subcommand to create our 4 tasks, so we get 4 threads, and then we use the tgroup for each command here, and we're going to send in, say, 4 arg lists right here, and we can call it multiple times. So here we're going to send in 4 more arg lists. So we're sending in a total of 8 arg lists, and then finally we'll say, okay, let's wait until all of those 8 arg lists are processed. When it's done, we're going to just use the print array command using the group name once again, and by specifying arg star and rvar star, we can see what our arguments were and see what our results are. I need to first change this, so we'll run the tgroup version. Okay. Now notice we're using considerably more CPU because we're running this in separate threads. In fact, if we show this, it'll show you how it's divided this up. It actually uses all 8 hyperthreads through the task scheduler. Now, in this case, we've only allowed for 4 tasks to work on this, so this is going to take a little bit of time. Now, if we type in, say, tdump count, we can see here's our 4 tasks, but each of them had to do 2 jobs because we only have a total of 4 tasks. If we type just tdump, we'll get the details on all of them, and you can see here the last result that each one produced. And let's run this again, and while it's running, again we can type in tdump dash result, and notice we haven't got the results yet. Now we've gotten our first set of results. Okay, now we have all of them, and we can see that the last result is now, for each task, we have the count as 2, and we have the second result that each one of them had to compute. Over here is our arg list that's saved in the group array so that we can introspect later if we want to see which task worked on which arg list. And let's run it another time, but let's change the tasks to 8, and then we're gonna bring up this guy again. And one of the problems with demonstrating this while I'm doing a screen record is that we're actually getting the most of the CPU is now going to the recorder program. But with 8 tasks working together, we'll see that we're now going to peg the CPU to 100%. Once again, we see now that we have 8 tasks. So far, each of them has only worked on one job. And now we have our results. So if we go back to this display, we could see that we got 99.99% of the CPU there. Incidentally, the screen record was glitching in the audio because we were using almost 100% of the CPU, and I guess the screen record doesn't run at a higher priority. Anyway, we're going to finish this up by showing you how to use this debug variable here. We have it set to -1, which if we bring up the documentation here, you can see that the putc command has several values that if you set the tdebug global variable to these values, with a -1 you suppress any putc output. With 0, that's the normal case, and on Windows you'll get a window will open up for each task that is running, and with a value of 1 you'll also get a debug trace of pulling items out of the queue, what the parameters were, and so forth. You can also set it to a value of 2 and 3. 2 will then redirect all the output. Instead of going to separate windows, it will go to the console window in Windows. That's also the default value on Linux. And a value of 3 would add a debug trace to that. Okay, we have added a couple putc statements over here, and we're going to change this value. We're going to start with the value 0 so that we should see some windows open up. So let's run this. Okay, it's finished, and one of the problems that we run into is that these windows don't come up exactly where we want them. So we've called a repositioning procedure to straighten them out. But what we can see here is that when we're running with just the 4 tasks, each one of them do 2 jobs, and the code that we had here printed out 2 statements, one before it called the sum routine, which was going to do the heavy compute, and then one afterwards. Okay, now we're going to run this again, but we're going to change the debug value here to a 2. And now we see that output, instead of going to those windows, will come to the console here. On Linux, it goes to a console regardless, because on Linux there's a bug and we cannot open TK windows, more than one TK window, without Tcl crashing. and it's finally done. As you can see, each message is prefixed by whichever task wrote the message out. Here was a run that I did without recording that took only 29 seconds instead of 38 seconds, and this is with running version 8.6 Alpha 6. Anyway, that just about wraps this video up. So, thanks for watching.